welcome to another session on these line commutated and PWM rectifiers. And here we will talk today about the rectifiers for electrolysers. Okay, we are in this week, the last week of our course, and we have included this as the one of the important application of the PWM rectifiers. Okay, we did not plan it initially, but later we thought it may be a good idea to include this one. So the what are these electrolysers and why are they important? So electrolysers are devices that split water into hydrogen and oxygen. We want to create hydrogen. Oxygen is very abundant. Oxygen is easily available in the atmosphere, but hydrogen is something which is going to play a very crucial role in today's energy systems. Okay, and so hydrogen is going to play a role in the energy storage and conversion, and also in the transport, because it is already used in several industries, but it is also going to play a very important role in the transport sector in the form of fuel cells, right? And so there is a lot of focus on production of hydrogen. In specially, we say that we want to produce green hydrogen. Green hydrogen means we want to produce hydrogen but through renewable energy sources. Okay, so this is something which there is a lot of work going on. Okay, now if you see here, what are the applications for these electrolysers? Of course, we want to produce the green hydrogen and reduce dependency on fossil fuels, but fuel cells is one of the biggest upcoming applications. Remember, hydrogens are used in existing industries in a big way. Okay, for example, ammonia production, during steel making, petrochemical and refining, hydrogen is used a lot. Okay, but in the transport sector, this has now got a lot of focus. Okay, so remember, in when you run a car or a bus or a train, something like that, you will either so if you want to run it on as an electric vehicle, so in EV you can have the energy source as the battery, which we know very frequently, but we also have fuel cells. It is possible. One problem with the battery is that battery uses, most of the batteries nowadays is like lithium ion batteries, and lithium is not so abundant throughout the world. Okay, all countries do not have a lithium storage in them. So people would like to have resources which are abundantly available inside their own country, because it helps in their own production of this. Suppose they want to make their own EVs, they would like to have a source of energy which is abundantly available in their own country. So remember, water is available very frequently. So from water we can actually make hydrogen, and that hydrogen can be used in as a fuel cell, as an alternative to batteries in electric vehicles. Now fuel cell, if you think technically, fuel cells and batteries, they are comparable technologies, but they are not the same. Fuel cells have higher energy density than batteries. What does this mean? It means for the same weight of a fuel cell and a battery, fuel cells can give more energy. Okay, so the total energy which is obtained from the fuel cell is more than the battery. So when you are thinking of the long distance electric vehicles like trucks and buses, which are going to run for a long distance, then fuel cell is more economical as compared to battery. On the other hand, when you need more power density, when you need quick acceleration, deceleration, then batteries are better than fuel cells. Okay, when you need quick torque, okay, high current, short time, high current, then batteries are better. But fuel cells are better if you want to take energy for a long duration. You are running steadily on the highway, for example in a bus or truck or even in a train, fuel cell based trains, right? So they are running steadily on the track, okay, with not much of acceleration or deceleration, frequent acceleration or deceleration. It's running steadily. Then fuel cells are more economical. So several studies have shown this. So fuel cell can be an alternate to the battery, or in some cases if you have a hybrid combination of a battery and fuel cell inside the electric vehicle, it can be very optimum solution. So that is why fuel cells have actually got a lot of attention, okay. In a fuel cell, what happens, you combine hydrogen and oxygen and to produce electricity, okay, and the byproduct is of course steam or water. So this is what happens in a fuel cell. So therefore the production of hydrogen becomes important. There are certain other advantages of fuel cells also, but there are disadvantages also. Advantages being that, okay, if you we have said that we want to charge batteries very quickly, but fuel cells actually, because if you have a hydrogen cylinder in certain petrol station, you can quickly replace the hydrogen cylinders, right? So the charging and discharging thing of the batteries, that can be that impact the charging time, okay. You need a quick charging of the battery with lot of stress on the power grid. Those things can be mitigated to a great extent if you have fuel cell. On the other hand, hydrogen is combustible, okay, so which is also a very dangerous thing, because the safety has to be ensured for hydrogen, large scale hydrogen production, transportation, installing it in the electric car or something like that. So that is where the challenges also exist. But many places you will see that fuel cell is considered to be a very important and upcoming application area of electric vehicles, okay. So energy storage, so stores excess renewable energy for hydrogen. So hydrogen can be used as an alternate to batteries, okay. And so grid balancing, absorbs separation from renewables, stabilizing the power grid. So these are some of the areas where the hydrogen can be used from an electrical point of view. Already remember, these hydrogens are used extensively in these kinds of applications. We are not going to talk about these things in this course, okay. So what happens in an electrolyzer, we will briefly talk about these things here. It's a much more elaborate and a huge area of knowledge. We are not going to talk about it, but basic idea here is that the core reaction involved in electrolysis is you split the water into hydrogen and oxygen, right? So you have an anode and you have a cathode, and you will put it in a solution, right? And then these two anodes and cathodes have to be kept at a different potential, okay. And so here the power converter comes in. So this is where the power converter comes in, okay, and it basically creates this DC source, which is again connected to the grid here, right? So this is what happens in a electrolyzer, and a rectifier is needed to create this potential between the anode and the cathode, right? So just to give you an idea, an electrolyzer consumes about 50 kilowatt hour of energy for producing 1 kilogram of hydrogen, okay. This we got from some of the articles. So just to give you an idea how much energy is required, okay. There are different types of electrolyzers like alkaline electrolyzer, proton exchange member, PEM electrolyzers, and anion exchange membranes, and solid electrolyzer cells. We are not going to talk about it. We will just show you some tables where we see that this alkaline electrolyzer, this is the most popular, okay. It is hydrogen purity is moderate, okay. Durability is also high, but the cost is very low, and it has a good scalability. and moderate power function. So the cost wise, so this is now currently this alkaline water electrolyzers, these have been there for a long time and they are now the most popular one. But this is also very important, proton exchange membrane. Okay, it is also it's considered one of the most important one. Others ones you can see in the internet, because there you can see much more in great details about different types of electrolyzers and how you can actually work with it. But in this lecture we will focus more on the power converters, right? This is where our analysis is. So electrolyzers require a stable and controlled DC supply to carry out this water splitting, and so we will take the energy, we of course will have this from the both the grid and the renewable energy. Okay, so we will use the power electronic converter, specifically the rectifiers. So what are the role of the power converters? First, you have to convert AC to DC, because we will need this DC for the electrolyzers, the electrodes, right? But we will also need a voltage and current regulation. Generally, the voltage at the output of the voltage at the output of the electrode. So if you see this one as the converter, this is the grid, and we are producing this one. So typically the electrolyzer is modeled as an RE circuit, okay, where R is varying, E is also varying. What happens is this will be going on varying, right? So what we need is a controllable output voltage. Okay, controllable output voltage, this is important. We have to change the voltage of the converter, right? And we also need a constant current. So we will do a CC, constant current charging. CC mode. Okay, we have to do this one because this R, the resistance of the electrolyzer, varies with aging and with the kind of solutions that we have inside, right? So we will have to have a current regulation. Typically we will say that I with less than 5% ripple, okay, less than 5% ripple is very much required. Okay, so that amount, so we will need a voltage and current regulation at the output of the electrolyzer. Of course, we would like to have integrated with the renewable energy sources, right? So instead of the grid, we can also connect a renewable energy source here. Okay, so so we can have a separate connection to the renewable energy source, right? Okay, dynamic control and protection. Of course, any converter requires a dynamic control, also the protection. If there is a short circuit or if there is a huge current flowing, it has to be shut off. And when we do this from the grid, we have to maintain the power quality and harmonic reduction, modularity and scalability. These are general requirements. And power quality, we know it is very important. But let us see that how much we are talking about here. Now this is where it gets interesting. Generally, large scale electrolyzers, okay, usually medium voltage, they are connected to the medium voltage grid. Okay, why is this? Because the power rating of electrolyzers can be often in the range of several megawatts. 10 megawatts, we have seen even higher than this. Okay, so and the currents, remember this, the currents are in the range of 2000 3000 amperes. So this is very important. From the electrical point of view, it is not easy to run a converter with hundreds or thousands of amperes. It's not such an easy thing. So not only that the devices have to be chosen properly, but also protection, because hundreds of amperes flowing, if there is any mistake, it will destroy everything on its path. Okay, so protection is very important for such a, okay, but the output voltage is generally in this range, okay, 600 to 1000 volt, which is very common. So in this circuit which we had drawn here, so this voltage can be like up to 1000 volt, but this current, so let me draw it with a different color. This voltage can be 1000 volt, but this current can be 2000 ampere easily. Okay, so 2000 amperes of current flowing into the fuel cell, into the electrolyzer, is something which is something to be kept in mind, and therefore this is very important in an electrolyzer. Also the power quality, right? Because you are going to reach 2000 ampere. Imagine the grid is going to support this one. Okay, so therefore we have to have a medium voltage grid. Okay, low voltage grid cannot support this much of current. Okay, it cannot supply this much of current, so we need a medium voltage grid, and huge amounts of currents, and the power can be 10 megawatt. So at the same time we need low EMI, low harmonics, improved power factor, and we also want a scalability, so modular power plants. Okay, so even going up to gigawatt level scale plants, okay, huge amounts of hydrogen to be produced. Okay, so this is something which one must keep in mind when designing or thinking about electrolyzer power supplies. So what are the typical power converter topologies for this? Of course, the most important is the thyristor rectifier. Okay, at the beginning of the course in module A, we had talked about this one. So module A, you will have to look into for both this one. Okay, thyristor rectifier and the diode rectifier with generally a buck converter or some DC-DC converter. And active front end is basically the voltage source converters which we use in, which we have studied in module B. Okay, and along with that we can also have active front end plus DC-DC power converters. Little part of this we have studied in module C. Okay, so the reason why we have this thyristor, so we had studied this long back. Okay, thyristor rectifier, and the reason why we have this thyristor rectifier is because of the high current. As I told you, the currents can reach to 2500 amperes of currents flowing, and the thyristor rectifier is one of the most robust converters. Thyristor rectifier is the most robust, and it can carry or withstand short circuit current for a long time. Okay, which is not possible with IGBTs or MOSFETs. It cannot withstand that current, and so thyristor rectifiers have been a very popular choice for electrolyzers. So this is one circuit, we have seen this one previously, 6 pulse thyristor rectifier or 12 pulse thyristor rectifier. We had touched upon this. Now we are seeing for the electrolyzer application. Here you can see that in a so this is the 6 pulse rectifier. This we have taken a delta star transformer, and then we have the thyristor rectifier. Okay, so this output voltage is adjustable, output voltage is controllable, and of course we must have a closed loop control so as to controlled current we have to allow to flow inside the electrolyzer. This has a problem with harmonics. We know that this has a problem with harmony because this will create 5th and 7th flowing through this one. Okay, so THD is poor, so this has a problem that the THD is poor, so we go to the 12 pulse. So this is where the 12 pulse comes in. You can see 0 degree and 30 degree phase shift between them, and then we have the two thyristors, and they can be actually connected in parallel. You can see these two thyristors have been connected in parallel so as to increase the current. Okay, so this is like output parallel. We were talking about this. So this is like input series output parallel connection. So increase the current, so the current level increases, and so we have the fuel, we have the electrolyzers here, coming at the load side. Okay, so this is typically the thyristor rectifier arrangement. What are its advantages and disadvantages? It is very robust and very well known. Thyristors have been there for a long time. In spite of the presence of silicon carbide MOSFETs, in some applications thyristors are irreplaceable. Okay, we cannot think of any other power semiconductor, okay, because it can handle thousands of amperes of currents. This is the biggest advantage. It is relatively cheap and quite efficient. Okay, so thyristors, the losses are not so high, it is very low. Okay, the problem is that it is much difficult to control. You remember, thyristors, once it is turned on, you cannot turn it off. It is only turned off when the current goes to zero, right? So it, compared to IGBTs can be turned on or off with the help of gate pulses. This is not true for a thyristor. And one big problem is the harmonic problems, because thyristors, when it fires at a certain angle alpha, the input side also gets affected. It draws a lot of reactive power proportional to alpha. It goes on taking reactive power from the grid, and also the total harmonic distortion and the harmonics which are getting injected is dependent on that alpha. So these are the disadvantages. So the other alternative is to put a 6-pulse diode rectifier or a 12-pulse diode rectifier along with a DC-DC converter. Okay, this is another possibility. Okay, why people have thought about it? The simple, because of the fact that now with a diode rectifier you do not have to change that alpha, okay, anymore, and the control part of it has been shifted to the DC-DC converter. So the DC-DC converter makes an output voltage which is regulated, and so that this current is adjustable. This current which is flowing through the electrolyzer is adjustable, and this is what so the diode rectifier is an uncontrolled device, so we do not have to control anything there, but we have to control the DC-DC converter. So this is an alternate, very close to thyristor, where thyristors we can directly control, but this is an alternate version of it. So what are the advantages and disadvantages? Okay, it is cheap and efficient. Okay, quite efficient. It's cheap because you have a diode bridge rectifier. It has a better control than the thyristor rectifiers, but it needs the DC-DC converter. Okay, this is the challenge. Okay, because the DC-DC converters have to be designed to handle such a large value of current. Okay, diode rectifiers can handle that current, it's not a problem, but DC-DC converters will have controlled switches inside them, IGBTs, and so we have to design those converters for keeping in mind of such high values of current. Okay, harmonic problems still exist because of the presence of the diode rectifier. Now we have the active front end converter. Active front end means you have a VSC here. Okay, complete VSC, and sometimes we have a VSC plus a DC-DC converter, and VSC can also do the same job, but of course, so we have seen this several times in module B and all. VSC can do it will maintain this DC link voltage, and it can control the current which is flowing in this DC link. So it has a high degree of controllability advantage. It's an IGBT based solution, so you can turn on, turn off. IGBT is very well established nowadays, and it has a very good harmonic performance. You do not have to take additional precautionary measure, because a VSC you can switch it in such a way that it draws sinusoidal current from the input side. What are the disadvantage? Fault performance is poorer. Okay, and fault performance poorer means that remember, 2000 or 2500 amperes of currents are flowing, and the short circuit withstand capability of the thyristor is much more than an IGBT or a MOSFET. Okay, so therefore during the fault you have to quickly turn off the devices, otherwise it will destroy. And there is the advantage of the thyristor rectifier is more than respect to IGBT. It needs more time to mature. Okay, yes, although we say that IGBTs are very mature technology, but at this level of current, say 3000 amperes or something like that, people commercially prefer thyristors till date. As of 2025, people still use thyristors as the main choice, first choice. Okay, so it's a costly one also. Now just a little bit of the electrical modeling and the equivalent circuit of the fuel cell. So this is the terminals of the fuel cell. Basically the voltage of the cell is V rev plus, so there is one constant voltage which is coming, all these voltages are coming from the chemical reaction that is happening, but there are also ohmic voltage drop, okay, which is designated by R, okay, and then there is also the activation over voltage, V activation, which is basically represented as an RC circuit, and V con is the concentration over voltage. Okay, so basically the chemical reaction that takes place in the electrolyzer is represented by equivalent one voltage source, one resistor, and one RC circuit in parallel, and another resistor. So this is the equivalent circuit of the electrolyzer. What, as an electrical engineer, we are interested in this circuit. We may not always look into the chemical reactions that is going on. We are interested in this circuit because we are going to inject a constant current charging into this circuit from our rectifier. So the rectifier is here, and with a closed loop control, this rectifier is going to inject this current inside the fuel cell. Okay, what is challenging here in this circuit is this thing, that these resistances are not constant. Okay, so at the beginning of the life, these values are at their lowest values, and over time, as the electrolyzer ages, R will increase due to the physical degradation. Okay, and so this increase causes the higher voltage losses for the same current. Okay, so therefore the efficiency, overall efficiency reduces, and that is why one of the reasons, as I told you, we must have a constant current charging. Okay, because the values here are going to change with time. Okay, at the beginning of the life and at the end of the life, all these values are going to change. So therefore for the fuel cell, we must remember that we need a variable voltage output from the rectifier with a controlled charging, controlled current charging. That is important. Okay, through which we will introduce that into the electrolyzer. And the most important topology as of now, as of date, is the thyristor based electrolyzers. These are the most important rectifiers which are used, and they are used usually, they are taken from the medium voltage or even from the low voltage also it is possible, but we must connect it because we are going to take megawatts level of power, okay, from the grid if you want to feed it into the electrolyzer. So it is usually, many times we take it from the medium voltage and we inject thousands of amperes of current. This is very important. Thousands of amperes of current which flows through the electrolyzer, and so we need this is one more application of a PWM rectifier or a line commutated rectifier. Okay, so with this we and here you can see some of the references which you can see in this. In summary, I just wanted to introduce this electrolyzer as an application of as a rectifier. We have not gone in details, definitely we have not gone into details of this, and we have not touched upon the chemical reactions, what happens, but the equivalent circuit as an electrical engineer is important to us, because that is how we will inject the current into the circuit. You can look into some of these references which are shown on the slide now. Thank you.